Hi.
Hello. Hi, everybody. Sorry, I saw Julia was struggling to get into the session, so I just wanted to make sure that was happening. Um, are we all good? Isn't it nice to have a marathon training session not in the evening? I have a lot more energy now. Um, can you also see my screen and hear me fine? Give me a thumbs up.
Yes.
Perfect. So guys, I asked you to go through your week 1 to 4 assignments slash exercises and see how comfortable or confident you are feeling reading the questions, doing the questions. Did anybody do that in the time since I've seen you? You can put it in the chat if you don't want to unmute, but just tell me if you did do that. Okay, no, I see a no. You haven't done it. Okay. It's okay if you haven't done it. If you did do it and you came across any problems, that's what I really want to know about now. Okay. Okay. If no one did it, that's cool. Um, I'm going to encourage you to do it after this session and definitely after tomorrow's session, because obviously that's your last chance to study for the exam. But yeah, let's get started in the meantime. Okay, so today is a marathon. Okay, we've got 3.5 hours in this session. I hope you can stay for it all, because obviously we're running through all of the test significance now. Um, and we're doing confidence intervals. So it's a lot of content. It's a lot of different things to learn. The way I've structured it is we're going to take two 10-minute breaks. Okay, so around an hour 20, an hour 30, depending on where we get in the content, we'll take a 10-minute break. And then we'll have another hour or so, a little bit of practice time, and then we're going to take another 10-minute break, and then we'll continue with practice. Okay. So this is a lot of hand calculation, and I am going to drill it. Okay, it's going to be annoying by the time we're done. Same thing tomorrow. So tomorrow's session is completely dedicated to regression. because regression is a very theory dense and understanding dense week. The actual practical regression questions, like the open questions, not actually that deep. It's the theory that takes a while to get through. And then for the rest of tomorrow's session, I'm going to test you on absolutely everything. So we're going to run through a lot of practice questions. All right, so just a reminder, when we're breaking down the question, these are the three things we're looking for: number of variables, level of measurement of the variables, and keywords. So I use these three colors when I'm doing this for each different kind of question, just so that you can see what we'd be looking at for each question. Okay. Okay, the easiest way to remember all of the different tests of significance and what they're testing is to group them by similarity. Okay, so especially if you feel like you're only understanding things now with this training and your exam is already, in 2 days' time, this is like, I recommend you do this to try and cram as much information as possible. So at the bottom, we've already done, like the blue one, we've done the one sample tests. Okay, and the one sample test is when we have an old population mean based on prior research, and we're testing it against a new sample mean to see if the sample mean is different enough from the old one. Okay, and then in the green, we've got the comparison between groups tests. Okay, that's your independent samples, two sample t-test, and your one-way ANOVA. Okay, so whenever they use the word compare, comparison, a significant difference between categories, all of that jazz, it's these two. The only difference between them, the two sample t-test allows you to compare two categories. The one-way ANOVA allows you to compare more than two categories. Okay. And then in the pink are our chi-square tests that can obviously be grouped together. And the reason is because they only deal in nominal ordinal variables. So if you're dealing with a test of significance and all the variables are nominal ordinal, it has to be a chi-square. The chi-square goodness of fit only has one variable. The chi-square test for independence has two variables. Okay. Anyone have any questions about this at this stage? No? Oh, last thing I want to mention for the comparison between groups tests, these are both only SPSS interpretation, no hand calculation involved. Okay, let's start with the two sample t-tests. And we're going to run through the Levene's test for equality of variances so you understand extra well. Okay, when you're reading a two sample t-test question, because you're testing a significant difference or a comparison between groups, and what you're comparing them on is the dependent variable. So their sample mean of the dependent variable. So if you read this, sleep researchers divide the group of teenagers into pubescent and post-pubescent age groups. So pubescent is 13 to 15 years and post-pubescent 16 to 19. They are interested in whether these two groups differ significantly in their average number of hours slept per night. Their expectation is that pubescent teens need more sleep due to their developmental stage. Formulate the hypotheses. Okay, so you should be able to identify that we're dealing with two variables. Okay, our unit of analysis are teenagers. Okay, and what are the two characteristics or attributes of these teenagers that are provided in this question? First, their age group. Okay. And the second thing is how many hours they sleep per night. So two variables. Age group is measured on an ordinal level, right? Because it's age categories. And number of hours slept per night measured on a ratio level. Okay, so independent, nominal ordinal, dependent, interval ratio. How do you know which one's independent, which one's dependent? It's like, well, ask yourself this question. Could their age group affect how they sleep? Or could how they sleep affect their age group? How much they sleep is not going to affect their age. Okay, so we know that age has to be the independent. It is the one that impacts the other. And when we write out our hypotheses, because we are literally comparing the population average of two groups, right, that appears in our H0, our basic structure is the population average of the first group, the pubescent group, is equal to the population average of the post-pubescent group. Okay. Basic structure, so it's equals to. Then your H1 has the potential to be either non-directional or directional, depending on what they've given you. If it's non-directional, you would just say that the two averages are not equal. Yeah. But because they have given you a little bit of information, it says their expectation is that pubescent teens need more sleep. Needing more sleep is an indication that they want you to make H1 directional. So pubescent teenagers sleep more hours on average than post-pubescent teenagers. Okay. Anyone have any questions about this? Any confusion? Cool. Okay, and there are two tests inside the t-test. Okay, you've got the Levene's test for equality of variances. Okay, remember variance is a measure of variability that you learn about in week 2, but you don't interpret the variance, right? You interpret the standard deviation instead, because the standard deviation is the square root of the variance. Okay, but this is just for the purpose of theory at this stage. Okay, so you've got your Levene's test, and then you've got your actual two-sample t-test. So it is the second test that actually allows you to conclude on your hypotheses, but you have to interpret the Levene's test on the path to interpreting the t-test. Okay. So what this means, because you've got these two tests involved, you're going to have two p-values in the output that you need to interpret. Okay. If you look at the hypotheses of the Levene's test, okay, they look just like the hypotheses of the t-test, okay, but instead of mu, which is population average, they deal with variance, which is sigma squared, okay. And the H1 of Levene's is always non-directional, so it's that the variance of the two groups are not equal. Okay. What is variance doing in a test of means? Okay, why does it matter? So what we're trying to establish with this test is a significant difference between groups. Okay. Now I want you to imagine I'm trying to say that Dutch IPCOM students are significantly different from international IPCOM students on their GPA. Okay. Well, how can I just look at their two group GPAs and be like, oh yeah, these two GPAs are far apart. Cool. They're significantly different, without looking first at each group on its own. So I look at the Dutch students and I look at, okay, what's the variety in GPA amongst the Dutch students? Because you could have everyone hovering around 7.5, right? Or you could have some really high achievers and some really low achievers. Yeah, so you need to figure out how dispersed the group is and then do it for the other group. Because if internationals if internationals and Dutchies are both diverse or varied in their GPA, it's going to be harder to say that they're significantly different from each other. Okay. So what we want to establish a significant difference is that we want the means to be far away. So we want the two groups to actually show that they're far apart in their GPA. But then we also need to show that each group is homogeneous. So Dutch students are achieving similarly, and international students are achieving similarly. And then you can say that they're significantly different from each other. Okay. On a more personal, like to think about it more personally, say you want to make a statement that, the Dutch and German people are really different from each other on whatever it is. Well, if Dutch people are diverse, if the Dutch population is diverse and the German population is diverse, which means a lot of them are like each other. There are Germans who are like Dutchies and Dutchies who are like Germans. Okay, do you see how that diversity makes it really difficult to establish a difference? Whereas if the Dutch population is Dutch and the German population is German, okay? They are similar, they are homogeneous inside themselves. That makes it easier to say that they're different. Does that make sense? Like the whole why we involve variance in this.
So is it to look at the differences within the group to see if they're like the same within the group to compare them then? Or
Yeah. You look at within and between the groups. So you establish that the groups themselves are homogeneous, and then you establish that they're far apart. So two homogeneous groups that are far apart. So it's within and between.
okay, thank you.
Okay, so I just didn't emphasize this, but I'd like to say so. So because you've got two p-values to interpret here, it's the second p-value that actually concludes on your t-test. Okay, so because you've got Levine's hypotheses, the first p-value is going to conclude on Levine's only. Second p-value will conclude on your t-test. Okay, so visually, this is what it would look like if the two groups had equal variance versus unequal variance. For equal variance, you can see that if you look at how far apart, how spread out the dots are, they're pretty evenly spread out, both of them. So they could be both all squished together or both spread out, but the point is they're equal. Whereas the one on the right-hand side where they're not equal, we've got one homogeneous group and then the other one that's diverse. Okay. So whether the variance between the groups is equal or not, we include in the math.
Sorry, do we need to oh, you're gonna talk about this now. Nothing then.
What's the question? Do you need to interpret output?
No. Do we need to state the H0 and H1 for Levine's test?
It's not automatic that you need to state it. They will ask you a specific question saying, please state the H0 and H1 of the Levine's test.
Okay.
Yeah. But if they don't specifically ask, you actually don't need to. But you still have to take it into account when you're interpreting. You just don't have to state. Okay, so if we look at this output for two sample t-tests, it does reflect how the output looks if you have the newest version of SPSS. So the Levine's test is circled in purple, and you can see it's actually sitting below the t-test, which is weird. But depending on your version, the Levine's test should actually be like here next to the t. But anyway, so if we break this output down, the first box that always appears for all your tests, all your analyses, is going to be statistics, meaning your sample statistics, your sample size, your sample means, your sample standard deviations. Okay. And because we're comparing means, like with the t-test, if you look at these sample means, right? If you look here, we've got our variables. Oh, your variables are always present, by the way. So theme of YouTube video is our independent, and we're comparing entertainment versus information videos, and we're comparing them on number of likes, mean number of likes. So if we look at the sample means, you can see that the entertainment videos have a much higher sample mean number of likes compared to information videos. So this already gives us a sense that we're going to be rejecting the H0 because these two means are clearly not equal. Okay, but you cannot make any conclusions based on that alone. It's just good to look at. It's also good to look at, especially if you have a directional H1. So if specifically they said that one group is going to be higher or lower than the other, you need to make sure in the sample mean that the correct one is higher or lower. Cool. Once you've done that, the next thing you're going to do is the Levine's test. That comes first. Okay. So in my case, I have to skip over this and go straight to Levine's test for equality of variances. Now, I want you to pay attention to what it says here, equal variances assumed. Okay, and if you look up to this box here, it says equal variances assumed and equal variances not assumed. Okay. These two rows are the H0 and the H1 of the Levine's test, right? The two variances are equal. The two variances are not equal. So back to Levene's test. When you find your p-value, which is here, and it is less than 0.001, so it is significant. Okay, it's lower than alpha, so we reject H0 of Levene's. If we're rejecting H0, that means we're rejecting equal variance as assumed. Okay, so we reject this top row and we select the bottom row that's got the red thing around it. That is how you interpret Levene's. You look at the p-value, okay? If it's low, you reject H0, accept H1. Okay. A simpler way, if you don't remember the H0, H1 situation, is if P is low, stick with the bottom row. If P is high, stay high. All right, so now that we've got the correct row in our output, now we can actually interpret the t-test. Okay, so our test statistic is going to be 7.421 or 7.42. Okay, and then we have to choose between one-sided P and two-sided P, and that all comes down to whether your H1 was directional or non-directional. Because we don't have any other information about this particular example, right, we're just going to call it non-directional, just assume. So we'll select the two-sided P, which is significant. So now we can actually reject the H0 of the t-test and retain the H1, accept the H1 that says that these two means are not equal. Now I want you to look at all the text that I've put on the side. If you only receive output, because notice we didn't receive any like question text to look at this output. I can already create my hypotheses only from this output. How do you do that? Okay, well, first you need to know your basic structure of your hypothesis for a t-test. You can see that in the title, it says independent samples test. So you know what test it is. Basic structure. Population average of group 1 is equal to population average of group 2. What are the groups? Okay, well, that depends on your variables. Your variables are always present. So group 1 is entertainment, group 2 is information, and population average of what? Number of likes. Okay, so H0 is that they're equal. H1, that they're not equal. And then you can interpret, you can conclude, and you can do an entire question just from being given output. Okay. Anyone have any questions about that, about this? No? Okay, that's good. And we can move straight into the one-way ANOVA. So your ANOVA stands for analysis of, oh, yes, Julia, what's up?
So for the two sample t-test,
Yeah.
it's right that there are no hand calculations and they would just give us SPSS output, but there's nothing more to know.
Nothing.
Okay, thank you. I just want to make sure.
Theory-wise, the only thing for the two sample test is the Levene's test. But that's it.
Okay, thank you.
Okay. So ANOVA analysis of variance. Okay, you can see, okay, if they're analyzing variance again, it's because we're trying to establish a significant difference between groups. So we have to involve variance once again. And your test statistic for the ANOVA is the F value. Okay, so far we've had like a one sample Z test. The test statistic is the Z value. For the T tests, it's the T value. So this we have the F value. The ANOVA is an extension of the two sample t-test. Okay, so like everything, when you're breaking down a question, everything is going to point towards these two tests. Okay, the only thing that differentiates them, that makes you choose an ANOVA over a t-test, is how many categories they actually want you to compare. Okay, if it's more than 2, it's an ANOVA. Okay, and the ANOVA includes a post hoc test called the Sheffer test. Okay, so the point of this is that when you run the ANOVA, it just tells you, like, yes, there's a significant difference between at least 2 of the groups. there's a difference somewhere. Say like you're comparing 4 categories and it says, yes, there's a difference somewhere. So the post hoc test is needed because it gets more specific about which 2 groups exactly are different. So it almost like it runs a bunch of 2 sample t-tests, comparing 2 groups at a time to see which ones are significantly different. Okay, ANOVA has a little bit of theory involved, all about variance. So we look at this example. 30 subjects in a sample are randomly assigned to 3 groups. All 3 groups read an article on the environmental policy of the city of Rotterdam. Okay, group 1 reads a negative article, group 2 reads a neutral, and group 3 reads a positive article. So you can already assume that what they're trying to ascertain is after these 3 groups have read this article that has a slant on it, is there a difference between them on their attitude towards the environmental policy? Okay. So when we talk about variance in ANOVA, we have 3 types of variance that we speak about. The first one, the first bullet point, the total variance, which is the normal variance that you learn about in week 2. And that's how much all the X values are varying around the mean of the group, the whole group, okay, the entire sample. Then you look at the variance between the groups, okay? So this image here, the variance between the groups shows the distance between each group mean and the overall mean that you look at for the total variance. Okay, so these arrows, this is the distance between the yellow group's mean and the grand mean, the green group and the blue group. Okay, so this gives an indication of how far apart the groups are. And then the last one is variance within groups, which looks at how much the X values inside each group varies around their own group mean. Okay, so the variance within groups, if you only pay attention to yellow, it's talking about how dispersed these yellow diamonds are inside that group. Okay. So essentially what we want to establish with variance is the groups are far apart, high between group variance, and then inside each group that they're pretty homogeneous. So we actually want low within group variance. Okay, remember what I said. If the Dutch population is very Dutch and the German population is very German, that indicates low within group variance. And then once you've established that, you want to prove that Dutch and Germans have a very different attitude on a particular thing. Okay. Any questions about this? Okay, so this is just a visual for the between group variance. Okay, so when your between group variance gets higher, on the left-hand side, if you look at the distances between the groups or from the group means to the grand mean, yeah, you can see there's smaller distances, whereas on the right, the distances are larger. Okay, so do you see on the right-hand side, we would be better able to say that these 3 groups are different from each other. Okay, higher between group variance. Okay, and for all the tests, when our test statistic gets larger, we're more likely to reject H0, by the way. So remember, when our obtained value is greater than the critical, we reject H0. So as our obtained value is getting larger, we're more likely to reject. So what happens when your between group variance is getting higher, okay, your F value is going to get larger as well. A large F value will indicate a low P value, which would mean reject. Okay, and this is representing within group variance. So if you're looking at each group individually, on the left-hand side, you can see that the diamonds are a bit more squished together. On the right-hand side, the diamonds are more dispersed. Okay, so what we want is actually the left-hand side. We want a low within group variance, low variation inside each group. And similarly, when our within group variance gets lower, our F is also going to get larger. Okay, which is just the opposite of what they've written here. And let's just see. So if our variance within groups gets larger, okay, that means that diversity is increasing inside the group. Then our F is going to get smaller, which means more likely to retain H0. Okay. Okay. So we've got a little formula that includes between group variance and within group variance. That's how you calculate F. Our between group variance is represented by MSV, which literally means between groups mean square. So MS is mean square. Within groups is MSW. When we calculate the F value, this is how we would do it. This is on your formula sheet, by the way. So if you're in the exam and they ask you if your between group variance gets larger, what happens to your F value? And you don't remember, like from studying, you can always actually play with the math, because the math will tell you. If let's say your between group variance is 5 and your MSW is 1. Okay, 5 divided by 1 is 5. So let's play with the numbers. Let's make MSB get larger between group variance. Okay, let's make it 10. Okay, 10 divided by 1 is 10. F just got larger. Yeah? Let's play with MSW. Let's make MSW get larger. So we were working with 5 and 1. Okay, let's make MSW 5. So 5 divided by 5 is 1. So we went from an F value of 5, we increased MSW and it became 1. So F got smaller when MSW got bigger. Okay, so you can always play with the math like that. But is this making sense so far? Okay, look at an ANOVA example. So just from this one sentence, I should be able to, or you should be able to discern it's an ANOVA from the get-go. So how do people from Belgium, Spain, the UK, and Norway differ in their level of happiness? You should immediately notice that they're comparing 4 different groups. Okay, and that's all you need to know it's an ANOVA. Okay, your H0 would be that all, in this population, all 4 countries have an equal mean of happiness. And for your H1, we keep ANOVA non-directional. Okay, why do we do that? Well, we have 4 groups that we're comparing here. If we had it directional, what we'd have to do is say that Belgium has a greater average than the UK, but Spain is less than Belgium, and Norway is more than Belgium, and you'd have to basically have a directional hypothesis for every possible combination of categories, which is time consuming and useless. So we keep it simple, we keep it non-directional. The 4 countries do not all have an equal mean of happiness. At least one group mean differs from the others. Okay, and the first table that'll pop up is your ANOVA table, which, as you can see, has a p-value and it has an f-value and it has a mean square column. You should recognize this from the previous slide. Mean square between groups, mean square within groups. Okay, so from your formula, that is your MSB, that is your MSW. And if you put it into the formula, you would get your resulting F value. Okay. And to interpret, we look at the p-value. Okay, So because it's lower than alpha, we reject this H0 and we accept the H1 that the 4 countries do not all have an equal mean of happiness. Great. So which countries are significantly different from each other? We don't know yet. And this is why we look at our post hoc. Okay. The only columns that matter to you in your post hoc are your p-value column, okay, your seg column, and your mean difference column. Okay. What you look for are the p-values that are significant, so lower than alpha. So if you look at the first one, 0.997, that's too high, so we ignore it. Doesn't matter. The next one, 0.001, that's low. It matters. That was when, if you follow it to the left, that was when Belgium was compared with the UK. Okay. So now that you've established that there's a significant difference between Belgium and the UK, you need to have a look at the mean difference number to establish which of those countries had the higher or lower average. I don't care what the number is, so the fact that it's 0.211 doesn't matter. Only notice whether it's positive or negative. Okay. So because it's positive, that means that Belgium has the higher mean. So the sentence that you would use to conclude is that Belgium has a higher average happiness compared to the UK in this population. Okay. And that's the first interpretation, and then you continue moving down the list. Another significant difference. That was Belgium versus Norway. Now your mean difference is negative. That means that Belgium has a lower average happiness than Norway in the population. Okay. And you keep going until you've interpreted all the possible combinations that are significant. Okay, watch out for duplications. They will be duplications. So the first p-value we said was Belgium versus UK. And you'll notice down here, UK versus Belgium happens again. Okay, duplicate. Don't report them both. All right, so once you've made your way down the list, it's always a good idea to notice if there's any situations like this, where for the UK, all of the p-values are significant, and same for Norway, all of them are significant. Okay, and if you look at the mean differences for the UK, all of them are negative, and for Norway, all of them are positive. What this means in terms of interpretation is that the UK has, like, significantly has the lowest average happiness compared to all the other countries. And similarly, conversely, for Norway, Norway is on average the happiest country in this population. Okay. Does all of that make sense? Does it confuse anybody? No, that's good. I know a lot of you, this is repetition from the SPSS training, but listen, repetition can't hurt in stats. Yes, Julie.
Yeah, sorry, I actually do have a question. So in the SPSS test that we did earlier this week, I ran an ANOVA test. I hope I did it right. But then all the outcomes from the significance and the difference in groups were all like 0.000, 0.001.
Mm.
So then I thought I did something wrong, but I don't know about the other people in here, but I was pretty sure it wasn't a ANOVA test, but it looked weird to me that everything was significant. But how do you interpret it then?
Well, first things first, you know you're going to interpret all of them. So the first thing to do is probably to cross out the duplicates so that you're not reporting anything twice.
Mm-hmm.
And then I would pay attention to what I just said here, circled in orange and purple. Have a look at the mean differences. Is there anyone where they're all negative or all positive? Because that'll give you which group has the highest average and which group has the lowest average, because that's always a good interpretation.
Mm-hmm.
And otherwise, other than that, there's no other like more efficient way to interpret than to just go significance by significance to make sure that you've reported everything, because you do
Okay.
need to report everything that's significant for an ANOVA. It's
Okay.
not like the crosstabs where you can pick and choose for your conclusion. You actually do have to say everything.
All right. Okay.
Yes, Laura?
I have a follow-up question. Is it necessary to state that there's a pattern, or is it enough to just say, like, yeah, Norway is on average significantly happier than the other countries? So do we have to say we can see a pattern, like, or does that not matter?
I'm not sure I understand your question. The most important thing is that every single significant p-value is accounted for. So the way I've done it here with UK and Norway is I've basically just like grouped a few together to be able to conclude in a more efficient way, so that I don't have to state every single one. But the way I do it, the way I group it, still accounts for all of it. So yeah, I'm not sure what your question is. Can you repeat maybe?
Yeah, so in the lecture they said that we have to either just kind of like name 3 rows of the ANOVA, or kind of like identify the pattern. So I was wondering if it's like necessary to, if there is a pattern, for example, as Julie said for the SPSS test where everything was like significant, if you would then need to say like we see a pattern and that's the pattern, or if it's just enough to just point out where the significance is.
I see. Yeah, okay, I see. If they're all significant, you can definitely say, well, there's a significant difference between all of the combinations of groups. Because that is a pattern, you're right. So that's, yeah, identifying a pattern is basically finding a way to group the significant results together. So, yeah.
Okay, thank you.
Okay, so looking at an ANOVA question, this screenshot is from your week 6. I don't know if it's an exercise or an assignment, but anyway. So you had to create a new variable age groups where you basically, the new variable now is measured in these age groups. And then for C, if you want to know if people in different age categories differ significantly in their level of reported happiness, which test do you have to use? So for B, they made you get the level of measurement, right? So age groups is going to be ordinal, obviously. And the variable happy, I would bet money, is probably interval. It's possibly a ratio depending, but probably interval. So it's showing you have a categorical IV and a continuous DV. And then it wants to know about a significant difference between the categories. Okay, so at this point, you don't know if it's a one-way ANOVA or a 2-sample t-test, right? Until it asks you about doing the different age categories and how many age categories were in the variable. There's 6. And because there's 6 and not 2, you would do an ANOVA. If in this question they said, if you want to know if people in age category 1 differed from people in age category 6, which test would you use? See, now, because you're only doing 2 categories, that would be a 2-sample t-test. Okay. So ANOVA, I think, is actually quite easy to identify in the question. And please don't get confused with number of categories versus like number of variables. Okay. So remember, there's only one independent variable, and in this example, it is age. Okay. The fact that age is measured in 6 different categories, okay, that's different. So we're not dealing with 6 independents. We're dealing with 1 independent with 6 categories. And yeah, okay, always non-directional, cool. I've kind of said all of this already. Okay, and someone brought this up the other day. Is an interaction effect. So, and how is it different from a confound variable? That's what is the question. So when you have two independent variables, you would do a two-way ANOVA, which you do not do in this course. You do it in your second year quantitative course. Okay, and it's called an interaction effect when your independent variables work together to produce a particular effect. So what it would look like is that something like country of residence has a particular effect on happiness, or like whichever country you're from, combined with whether it's urban or rural, will have a particular effect on your happiness. Okay. So it basically just looks for a combination of categories that's going to produce an effect. Because maybe there'll be a significant difference between country of residence, so where you live, there'll be a significant difference between where you live on your happiness, but only if you live in a rural area. Okay.
Can you can you explain maybe what is then the difference between this and a confound variable?
Confound variable.
Or is it just when it's very clear that it's an ANOVA?
Yeah. So, well, with a confound variable, it's basically saying that you find a correlation between two variables. So let's say, for example, you find a correlation between country of residence and happiness. Okay, but that shouldn't make sense. So with the confound variable, it's when you have a correlation that does not make sense. That independent should not affect the dependent at all. But then you realize there's a third variable that actually affects both of them and explains why there's a correlation in the first place. Okay. Yeah. In this situation, this is country of residence would have an effect on happiness. That doesn't need to be explained. It exists already. We're just adding in another independent.
Oh, okay.
Yeah.
Okay.
Okay, now for the chi-squares. How are we doing on time? Doing very well. Okay, so your chi-square tests are your nominal ordinal tests, also called your non-parametric tests. Why non-parametric? So all of the other tests of significance deal with a population parameter, specifically the mean. Okay, so your one sample test, your two sample test, and your ANOVA, they all deal with means. And because your chi-square tests only deal with nominal ordinal, the mean is not possible for nominal ordinal variables. So it does not deal with population parameters. It's non-parametric. Okay. Your chi-squares, they both start by asking how we expect our sample data to look if H0 is true. So if we recall, our H0 is always this based on prior research, what we already know about this population. Okay, it is our expectation. This is our baseline. And then we take a sample and we observe our sample, we calculate whatever, we have a look at it. That is what we observe. Okay, so we have this expectation coming in, and then we actually observe what happened. Right, so this expectation versus observed is what we are always looking at with the chi-squares. And that's represented by FE and FO. Okay, so E for expectation, O for observed. The F stands for frequency. Okay, why frequency? Because we still have to work with numbers, like nominal ordinal variables, not measured in numbers. So instead of looking at the actual measurement, so like say it's measured in nationality, we can't put South African, Dutch, German in a formula. So we look at how many people in the sample fit into those categories, and we work with those. Okay. The larger the difference between what we expected based on previous research and what we actually observed, okay, the less likely H0 is true. Okay. Remember, H0 is always the expected. So if there's a huge difference, we're going to reject that H0, reject our expectation. Okay, let's go with the goodness of fit. Okay, our goodness of fit is dealing with one variable, and basically we're testing if a certain distribution of the population is still true. Okay, so basically we have prior research that tells us that the population is distributed in a particular way. Okay, so if you look at this example, the variable that we're looking at is EUR students' satisfaction with campus facilities, and maybe based on a survey that they did last year, this is what they would expect from the population, that 80% of them are satisfied, 10% are not, and 10% have no opinion. Okay. So that's what we expect from it. And then whatever they provide you with in the question, this frequency table, that is the observed. Okay, so they expect these percentages are from the survey from 2025. The frequency table they give you is from 2026, brand new sample. So if 100 out of the 150 were satisfied in 2026, if we made that into a percentage, 100 divided by 150, multiplied by 100, we would get about 66%-ish. Okay, that means in 2026, 66% are satisfied. What was the expectation again? 80%. So just from looking at those percentages, we're like, there's definitely a difference between what we expected and what we observed. Okay, but that's just for funsies. That's not how you conclude. That's not how you do the chi-square, which we'll get to in a second. I just want to point out what's going on in the question, because this is exactly what the question would look like. Okay, how many variables? Only one. Okay, and it can have any number of categories. So this particular variable has 3 categories, but it could have 6. Doesn't really matter. Okay, level of measurement has to be either nominal or ordinal. And the keywords, okay, the text will always say that, it'll always break up the population into percentages and put a percentage inside each category. Okay, our H0 is copy-paste what they gave us in the text, because that is our expectation, that's our baseline, that's our starting point based on prior knowledge. So we just write it all out. And our chi-squares are simple and non-directional. So we just say that it is not true, that, and rewrite all of it out again. Okay, to actually do your chi-square goodness of fit. So you start out with your observed frequencies, okay? So, sorry, these are your observed frequencies. They're given to you. You don't change them. You don't touch them, okay? What you are responsible for calculating are your expected frequencies. So if we observed, if we expected 80%, here we go. We expected 80% of the sample to be satisfied. What was that? So 80% of 150 is 120. Okay. We expected 10% for not satisfied. Oh, whoops. My keyboard. Not satisfied and no opinion. Okay. And then we find those are our expected frequencies. So for satisfied, our FO was 100 and our FE is 120. Okay. And so you've got an FO and FE for every category. Pretty easy to calculate that. Once you've got your expected frequencies, now you can move on to your chi-square formula. Okay, there we go. So if you look at your chi-square formula, notice that your sum sign is on the side of the fraction. Okay, what that means is that you start with your brackets. Okay, you start with FO minus FE squared. So it would be 100 minus 120, square it. And the next thing you do is divide by FE. Okay, so you would divide by 120. And then you put it aside. Then you do that for every single category, for not satisfied and for no opinion. And then once you've got those 3, you can do the final thing, which is to sum them up. Okay, so the number of categories you have for your variable is the number of times you're going to be doing this fraction. Okay. So you do your calculations and you end up with your chi-square obtained, which is your 20. Okay, same process as every hand calculation test. Once you have your obtained value, you need to go and find your critical value. Okay, so you need to know your alpha. And the chi-squares are super simple, right? We don't have to think about direction of H1, none of that. All we need is our degree of freedom, because as you can see, it does appear. And for the goodness of fit, our degree of freedom, one sec, our degree of freedom was number of categories minus 1. Easy peasy, 3 minus 1. Okay. The degree of freedom is 2, alpha is 5%, critical is 5.99. We ask ourselves, is 20 greater than 5.99? Yes, it is. So we reject the H0 and accept our H1, that in the population, it is not true that 80% are satisfied, 10% are not, and 10% have no opinion. And that's it. So you start with calculating your expected frequencies. Then you can do your chi-square formula and get your chi-square obtained. Then you look for your critical, you compare them, and you conclude. Any questions about the goodness of it? All good. Lovely. You guys are getting things really fast. It's really nice. Okay, last one before we take a break. Your chi-square test for independence. Okay, your chi-square test for independence is also a spiel where you're going to use your observed versus expected, but you're going to get your expected a little differently. Okay, if you are able to identify that you've got two variables that are nominal ordinal and they want a test of significance, it's going to be this chi-square test, easy to identify. But if you need a little bit more than that, the key word that's used for chi-square in this case is relationship. Okay, because this test is based on a crosstabs, the crosstabs also uses the word relationship. Okay, so they're friends. The only difference between them, in fact, is do they want a test of significance from you, or do they just want a simple conclusion from crosstab? Okay, that's how you would differentiate. And because it's about a relationship, that's what appears in your H0. So your basic structure of H0 is that there's no relationship between the two variables. And your non-directional H1 is that there is a relationship between the two variables. And that's it. Pretty straightforward. Oh, something I wanted to point out. So if you look at this little text here, sleep researchers wanted to know whether the teenager's biological sex, male, female, has a statistically significant relationship with the number of hours they sleep per night. So if I took out statistically significant and I only said relationship, that would be a crosstabs question. But because I've included statistically significant, I'm indicating that I want you to do inferential stats. I want you to do a test of significance. And the other thing I wanted to point out is that the second variable is the number of hours they sleep per night. Number of hours can very easily be assumed to be a ratio variable. Okay, so the fact that I've specifically showed you how that variable is measured, and it's measured in an ordinal, on an ordinal level, I'm giving you that information for a reason. Okay, just like your chi-square goodness of fit, they will always give you your observed frequencies. And please don't touch your observed frequencies, like this 60, 80, 40, 80, don't touch. They are as they are. What matters to you is this total column. Okay, so your total column is basically how you're going to generate percentages so that you can use those percentages to calculate your expected frequencies. Okay, so if you think about this, right here, they're trying to establish if there's a relationship between gender and poetry liking. Another way of saying that is there a difference between the men and the women in terms of whether or not they like poetry? Okay. Now, if you look at the total people in the sample who like poetry, 140 people like poetry and 120 people don't like poetry. Okay. Let's look at 140. If there's no difference between genders, which means there's no relationship between gender and liking poetry. Okay. So that's your H0, right? If we applied that, if we created a percentage here, so 140 out of 260 like poetry, right? So that's 53.8%. If 53.8% of the sample like poetry, and we're not discriminating between genders, okay, then it should be true that 53.8% of the males like poetry and 53.8% of the females like poetry. Okay, because we're not discriminating. So once you've calculated your total column percentages, you need to apply them to each column total, okay, for the independent variable. So it should look something like this. So 53.8% multiplied by 100 males gives you 53.8 males. 53.8% multiplied by 160 females gives you 86.1 females. Okay. Then you use the second percentage, 46.2, and again, you apply it to each column total to give you 46.2 and 73.9. So do you see here what you did with this total column is that you created an expected percentage, okay, and then you use it to create your expected frequencies. Does anyone have any issue with this so far? Yeah, Julia.
I have a question because I found the formula in our, I think it was the lecture notes or my reading notes, I'm not quite sure, but I found this like formula for expected frequency, raw total multiplied by column total divided by grand total. What is with this formula, or is it like not right?
Can you say it again?
Row total?
Row total. Okay,
Row total
that's 140.
times the column total
multiplied by the column total, which is 100, I think.
and then divided by the grand total.
Grand total is 260. It's just an alternative method, I think. Because here's my calculator, okay, if we did it that way, so row total 140 multiplied by column total, which is 100, right? And then divided by grand total, 260. Yeah, you get 53.8.
Okay, perfect. So I could also use that.
You can. Okay.
Thank you.
I recommend using any method that makes the most sense to you. So I prefer this because I understand this in terms of expected percentages, and then I apply it to each column. So I go 140 divided by 260 multiplied by 100 to get my percentages, and then I apply. But if that other method works for you, please, by all means, it gets you the same answer. So it's all good.
Okay, thank you.
And then here, you've got an FO and an FE now for each combination. So for males who like poetry, FO is 60 and FE is 53.8. Okay. And because now you've got 4 blocks that you're going to be doing, right? 60, 80, 40, 80. You're going to be doing this fraction 4 times in the formula, and then you're going to sum up 4 values to get your chi-square obtained. Your degree of freedom is number of rows minus 1 multiplied by number of columns minus 1. Please just know that they're never referring to the total columns in your degree of freedom. They actually mean number of categories of the variable. So number of rows actually only refers to likes and dislikes, not total. So it's two rows and 2 columns. So 2 minus 1 multiplied by 2 minus 1. Any other questions about getting your expected frequencies? Does it make sense to everyone why these percentages we calculate are the expected percentages? Cool. All right, so you got 4 values to sum up, and you get your chi-square, obtain 2.47. Okay. Your degree of freedom is 1, and your alpha is 5% as always. So your critical is 3.84. So we're comparing 2.47 against 3.84. In this case, your obtained value is now smaller than the critical, so we do not reject H0, we retain it. In this population, there is no relationship between gender and poetry liking. And that's it. In SPSS, it's very, very simple. So it'll always produce a crosstabs. And often what they'll do is they'll be like, okay, open question 4.1, interpret the crosstabs. What are your initial conclusions? So they'll basically ask you to do a crosstabs interpretation first. And then the next question will be like, if we want to know if this is a significant relationship, which test would we use? And then it becomes a chi-square. And to interpret your chi-square, Okay, to interpret your chi-square, you just look for your p-value under chi-square tests, and it's significant, so we would reject this particular H0. If they only give you output and then they tell you formulate hypotheses and conclude, okay, remember your variables are always visible. So you can see it's a chi-square test and crosstabs, so you know that it's a chi-square test for independence. And so it's about a relationship between 2 variables. Your variables, your IV is always in the column, so it's country, and your DV is the row, so how often people worry about becoming a victim of violent crime. And you can do your hypotheses and you can conclude just from looking at that. Any questions before we move on?
Well, what did you say when you started this slide? Like when they're gonna ask you an open question to interpret the crosstab or something?
Oh, yeah. So they often just structure their open questions in a way where, like question 4.1, they ask you to say, okay, what are your initial conclusions looking at the crosstab? So they're basically asking you to do a crosstab interpretation, not a chi-square yet. And to do that, you would compare percentages going across. So you'd be comparing Belgium versus Germany, 3% versus 1.6%, yada, yada, yada. And you basically look at each one and compare. And overall, it looks like Belgians are more likely to be worried about being a victim of violent crime than Germans are. That's the simple, simple conclusion.
So that's when you just take, is this where we learned, like you take 2 samples and you say like, okay, so in Belgium, the worry about being a, whatever it is 3%, whereas in Germany it's 1.6%, and then you can already say people in Belgium will be more more worried.
Yeah.
Okay.
Yeah.
Thank you.
And then the next question will ask you about significance. And then you can interpret the p-value. Okay. All right, time for a break. Lovely. So it's 12:10, which means if you'd like to, you can let me know in the chat how you're feeling. I I think we have time to take a 15-minute break now, but if you'd rather just do 10 minutes and continue, please just let me know. I'm happy with either. It's a long session, so we're trying to pace ourselves a little bit. Okay. 10 or 15, guys, put in the chat. $15? Cool. All right, don't get too comfortable. But yeah, take a little break, have something to eat, have a snack. Cool. I will see you back then at 11:25. All right, guys, we're back. We're ready. Awesome. Okay. Let's go. Confidence intervals. Okay, so the only test of significance now that we have not looked at is the regression, which we're going to deal with tomorrow. But in the meantime, confidence intervals. This should be one of the questions in the exam that you get 3 points for. Okay, I don't want to see anybody losing any points over confidence. So confidence intervals are also called interval estimations. Okay, it is not a test of significance, please. What we are doing is we're estimating the population mean based on sample statistics. Okay, so we've taken a sample, we've run some descriptives, and we want to be able to estimate the population mean. Our estimation puts the population mean in a range. Okay, so it's always between this number and this number, between 1 and 10, for example. And because our range has 2 boundaries always, because it's lower and upper, it is always 2-sided. Okay, so there's no hypotheses, there's no like H1 or anything because it's not a test of significance, but we still do work with like Z values and T values in the T table and whatnot. So you need to know if it's 2-sided or 1-sided, and it's always 2-sided. An example conclusion would be, we can conclude with 95% confidence that the population mean for our studying ISA lies between 17.06 and 22.94. So it's super, super easy to identify these questions because they pretty much always use the word confidence. Okay, so if they say we want you to be 95% confident, that should indicate this kind of question instantly. What is your confidence level? What is that talking about? Okay, well, remember when I first explained what alpha is, I said that it's basically a 95% accuracy rate. Okay, so it reduces the possibility of making a type 1 error to only 5%. Okay, so that's what your level of confidence is when you're making this estimate of the population mean. If you're 95% confident, that means your alpha is 5%. If you're 98% confident, it means your alpha is 2%. If you're 99% confident, your alpha is 1%. Okay, and what does the alpha affect in a confidence interval? Well, in the formula, we work with Z and T critical values. And how do we find critical values? We always have our alpha. We always know if it's 2-sided, 1-sided. In this case, it's 2-sided. And we have a look in our table to find a critical value. Okay. So this is the only time in the entire course where our alpha can change. Okay. Every other situation, your alpha is guaranteed 5%. Confidence intervals, you need to pay attention to how confident they want you to be. As you can see, we've got 2 formulas here, okay? I just put 2 different ways of writing this formula, but it's the same formula in a sense. So this sigma m on the left-hand side, that is standard error, which as we know is sigma divided by the square root of n. Okay, tell me, what is the difference between these 2 formulas that you can see?
I think the first one you're going to be using the Z table, and the second one you're going to be using the T table.
Absolutely.
Sorry.
Yeah. So if we're going to use Z for one, T for the other, tell me, how do we decide which formula to choose? As far as I've taught you in the training, what is the key differentiator between using Z versus using T?
If the standard error or standard deviation is known, right?
Yes.
So I don't know which one.
It's true. It's the standard deviation. Okay. Whenever we are given the population standard deviation on a silver platter in the question, we use Z. Okay. That's true for all of the Z situations. We have to have population SD given to us. If it is not given to us and we only have sample SD, and that could mean they give us sample SD or we have to calculate sample SD, in those situations we have to use T. Okay. Is that clear for everybody? I think so. Clear. Lovely. So let's look at an example. If our sample mean is 20 and our N is 100, and let's assume sigma, population SD, is 15. Okay, so they've given it to us, we can use Z. With 95% confidence, we can say that the population mean lies between M subtract 1.96 SE times SE and M plus. Okay, so you'll notice in the formula there's a plus and a minus. So you have to do both, obviously, because your final answer will include two values. It'll be between the lower number and the higher number. So the minus gives you the lower number, the plus gives you the higher number. Okay, where did I get 1.96 from? Okay, before we look at that, let's look at the standard error. Okay, your standard error, sigma divided by the square root of N. And we have both of those values that was given to us in the question, so it's easy, 1.5. Okay, put it into our formula, right? Our sample mean is 20, we know this. And we will get our final answer. But coming back to 1.96, how did I go from having Z to having 1.96? Okay. So guys, remember this little treat, the Z table, that does not differentiate between two-sided and one-sided, which means you have to differentiate yourself. Whenever we're working with Z and we have a two-sided situation, so for the one sample Z test, it was a non-directional H1, right? We had to divide our alpha in half and then look for it because it's two-sided, account for both sides. So again, we are looking for 2.5% as our alpha, right? Because we want to be 95% confident. So alpha is 5%, divide in half, 2.5%, and the corresponding Z critical is 1.96. So as I said before, this is going to always be the case when your alpha is 5% and you have a two-sided Z situation. Okay, but be careful with confidence intervals because maybe your alpha is not going to be 5%, right? If they say they want you to be 98% confident, that leaves an alpha of 2%. And if you have to go look for your critical in the Z table, what do you have to do? You have to divide that 2% in half. Okay, and that means you're looking for 1%. And you can actually see it here. So on the right-hand side in the C column, here almost at the bottom, we've got, 0.0099. Okay, that's the closest we can come to 0.01, which is 1%. So if your level of confidence was 98%, your critical Z value would actually be 2.33. Does that make sense to everybody? Yeah, cool. So basically, I want to go back a little. In terms of what you actually need to do when you get a confidence interval question, your sample mean will either be given to you or, like if you have sample data for a T, you would have to calculate it. But anyway, let's stick with Z for now. They have to give you sample mean. They will give you M. They will give you sigma. Okay. What you have to calculate yourself is your standard error, which is nice and easy. And you need to go find your critical value based on your alpha. Put it all into the formula. It's an easy formula, and then you can finish. Okay. Now, if we have to choose T, look at this example. Assume that we have drawn a small random sample of EUR students and asked them how much time they spend traveling to the EUR. Okay, and we've been given a sample, lovely, with all the sample data. Based on our sample data, what can we state about the mean and the population? Between which values do we expect the population mean to fall if we want to be 95% confident? Okay, so again, They want you to use a 5% alpha. Okay, but they've given you only sample data, saying please deal with it yourself. There's no population SD in sight, so we have to use T. So from the sample data, you need to calculate your sample mean, and you need to calculate the sample standard deviation. Okay. So sample mean and sample standard deviation you already have in, and the last thing that you need is the T critical. So alpha of 5%. Let's go. We look at the T table, okay? No need to divide anything in half because it's organized. So we just choose proportion in two tails because it's two-sided, and we pick our 5% alpha, and our degree of freedom is n-1, which is 5. So our critical would be 2.57. Can someone tell me if our confidence level for this question was 99%, not 95%, what would the critical value be? Yeah, Julia?
I would say the 4.032.
Yes, exactly. So this one over here. Exactly. Because your alpha changed from 5% to 1%, you would look in the 0.01 column and your degree of freedom is still 5. So that would be your critical. Lovely. Okay, so yeah. You do your calculations to get all the values you need for your formula, and then you can put your values in. And remember to do 1 minus and 1 plus so that you get 2 answers. And your conclusion, we can now state with 95% confidence that in the population of EUR students, the mean travel time lies between 18.99 and 41.01 minutes. Okay, so easy. So yeah, if we have the 99% confidence level, so the 1% alpha, we would use a different critical value. So how would that actually affect the result if our critical value is larger? Okay, so before our critical was 2.57 and now it's 4.03. Let's see what happens mathematically. Okay, now our boundaries are 12.74 and 47.26. Before, it was 18.99 and 41. So what's happened to our boundaries is they've expanded to include more possibilities in the range. So how does that make sense? If we want to be more confident, so 99% confident, right, we have to expand our range. Okay, if we want to be less confident, we can shrink our range. Intuitively, this should also make sense to you. I want you to think about it like gambling. Okay, if you have to be 99% accurate or you're going to lose all your money, you have to widen your range of possible winning numbers. Okay, I want you to think like if you were to guess my age and I said you have to be 99% accurate. Okay, there's only a 1% margin for error. Then you're probably going to tell me, oh, I think you're somewhere between 23 and 35. Okay, so it's quite a wide range. Then if I say, oh, you only have to be 50% accurate, that means a 50% margin for error. So 50-50, you can be right or wrong. Then you might say, you're between the age of like 27 and 30. So your boundaries shrink because you're taking a lower risk. Okay, because you have a bigger margin for error. So one of the theory questions that they could pose to you is like, what would happen if we increased the confidence level? What would happen to the boundaries? You need to say that they would expand or that they would widen, and then you need to explain that a higher level of confidence basically means a lower margin for error. So you need to include more possibilities. Okay. What other value in the formula do you think could affect the boundaries? So think about it. The confidence level has to do with your accuracy rate, right? Your margin for error. What is another value that we talk about that affects how accurate we can be when we're generalizing about the population, or where we're trying to establish something about the population? Does anyone remember? Give it a try. Let me go to the previous slide so you can see the formula a bit better. Yeah. Okay, have a look at the formula. What else besides the critical value?
I think maybe the standard deviation, but I'm not really sure why I think that.
Okay. The standard deviation would definitely affect your boundaries. And it's because the standard deviation is a measure of variability, right? So it shows you if your data is more spread out or closer together. So if your data is more spread out, that's automatically going to increase your boundaries. So higher standard deviation means people are deviating more from the mean, more options. That is true, but there's something specific that I am looking for. Kind of two things. What do I say is like the most intuitive way we know that is really important when you're trying to generalize about a large group of people? It's the reason this is part of the formula, the sigma hat divided by square root of n. What is that inside the brackets? What's it called? Anybody?
Is that oh no, it's not the standard error.
It is the standard error.
Oh, it is.
It is. Sigma divided by the square root of n is standard error. And what is the point of the standard error? Right? Standard error is to include in the math that our sample is always going to have some degree of inaccuracy because it's not going to perfectly reflect the population. Okay? So inside standard error, how do we account for that accuracy, right? It's n, sample size. Guys, intuitively, we know that the bigger the sample size, the more accurate we're going to be generalizing. Okay? If I take a sample of 10 students, IPCOM students, and I want to say something about 300 IPCOM students, are you going to believe me? No. If I sample 100 IPCOM students and then I say something, then they'll be like, oh, okay, she sampled 100. Okay, so mathematically, that's true as well. The bigger our sample size, the more accurate we are. Because when n increases, standard error decreases. Okay. So same thing, it's got the same logic to it as the level of confidence, right? So if we are increasing our sample size, okay, that means we automatically can be more confident, okay? And because the sample size is giving us our confidence, we can shrink our boundaries, okay? So it's a funny thing that when you have a high confidence level, actual confidence level, your boundaries have to expand to allow more possibilities. But when you increase the sample size, like your confidence, basically, it's a different way of looking at confidence, but your boundaries are able to decrease. Okay, it's kind of like if you're guessing my age and then I start providing more information about myself, think of that as increasing sample size. And I tell you, okay, I started IPCOM quite a few years later than most IPCOM students. I did a 2-year master's degree as well. And you start calculating the years, then you start having a better sense of my age. Okay. So that's theory. You've got to know when one value increases or decreases, what happens to the boundaries. Yes, got a hand raised.
Yep. So But if we increase the sample size, wouldn't that mean that we have more chance of being wrong
More chance of being wrong?
about like guessing the
No. A bigger sample size always results in higher accuracy. Always.
Okay.
Yeah. So if you did it mathematically, let's do it mathematically actually. That always helps in case you don't remember. So let's do this little formula that's on our screens together. So open your calculators. And instead of n equals 6, let's make n equal 20 for fun. So we're going to increase the sample size here. And all the other, let's just do it for, let's do it for minus and plus. So 30 minus 2.57 multiplied by Okay, so your lower boundary should be 23.97. Oh. Okay, and your upper boundary should be 36.03. So do you see what happened is our boundaries came closer together. It became 23 to 36 instead of 18 to 41 because we increased sample size. It's almost like sample size increasing makes you more sure of the true population mean because literally you just sampled more. Does that make sense to everybody? If you get this theory question and you're really not sure, do it mathematically because the math does not lie. You might have trouble explaining why it's the case, but at least you'll get the right answer, especially if it's multiple choice. Okay, and that's it for the teaching time. Are there any questions about the content for today? Anything you need me to repeat? Okay, cool. Let's move on. Practice time. All right, guys. Whatever you're working on, whether it's digital or like a physical piece of paper, I would like you to actually answer all these questions and do your best to give proper explanations because they might ask you such things. But why I also want you to be able to explain the answers to some of these questions, even though they might only appear as multiple choice, is that if you can explain something, then you're much less likely to be unsure about what is the correct answer in a multiple choice. Okay, so go for it, and then please just say done in the chat when you're done. I'm right here, as usual. Alrighty, a few of you are done, so I'm gonna move to the solution. Does anybody want me to not move to the solution just yet? If you need another minute, just say so. No? All right, let's go through it. So your independent variable would have been continent, and your dependent variable is the legal media freedom score. Okay. You can also have said laws and regulations governing the media. It doesn't really matter as long as you identified the variable correctly. Okay, it is a one-way ANOVA, and the post hoc test is called the Schaeffer's test. Your hypothesis should have been, in this population, all the continents have an equal average legal media freedom score. Your H1 should have been, in this population, the continents do not all have an equal average legal media freedom score. At least one of the continents' means differs from the others. And your conclusion, we can reject H0 and accept our H1, but in this population, they're not all equal. Africa has a significantly higher mean legal score when compared to the Americas, Europe, and Oceania and Australia, respectively. Asia also has a significantly higher mean freedom score when compared to the Americas, Europe, and Oceania and Australia, respectively. There is no significant difference between Africa and Asia's mean score, and there are no significant differences between the Americas, Europe, Oceania, and Australia, respectively. I have worded this to cover all the differences efficiently. There's nothing wrong with different wording as long as you have covered all of the significant differences. Okay, so when I've said like Americas, Europe, and Oceania and Australia respectively, I mean, I'm speaking about each of them on their own. Your MSB and your MSW are there, and your F value and your P value. Okay. How did you guys do on this one? Did you get it all right? This is good to see. Lovely. Next question, let's go. Okay, solution done. Okay, your conclusion should be, we can conclude with 98% confidence that the average level of contentedness with their romantic relationship quality in the population of women older than 45 lies between 5.83 and 6.77. That should be your calculation. For 2, the interval would shrink, so the boundaries would get closer together. This is because a larger sample size provides more accurate information to be able to estimate the population mean. And then for 3, the interval would shrink as well. Boundaries would get closer together. This is because there is a larger margin for error allowed. Alpha is 10%, which means that the estimation can be riskier. Okay. Obviously, for 2 and 3, your explanation doesn't have to be like bar for bar what I wrote. It can be explained in your own way, as long as you're explaining the same concept or the same logic. Did anyone have any issues with this? No? That's really good. Okay, let's move on. Go for it.
I have a question.
Yeah.
So, I'm right now struggling with calculating the expected frequency because
Okay.
here the formula, like the one I told you about, the row total multiplied with the column total divided by the grand total, could not work, right?
Correct. You're thinking about a different test,
Oh,
right? Yeah. So what
oh
test am I
yeah.
working with here?
I wanted to do the goodness of fits, but I mixed it up.
Yeah. So how we calculate our expected is different for the goodness of fit versus the test for independence. Yeah. The goodness of fit is way more straightforward.
Okay.
Do you remember how to do it?
I wrote it down, but not
Okay.
really. Like,
Okay. So why I say it's way more straightforward is they provide you with your expected percentages in the question. So these percentages that I gave you,
mhm.
those are the ones you use to calculate your expected frequencies. So it's only in the test for independence where you actually have to calculate expected percentages and then calculate expected frequencies.
Oh, okay. Yeah, I think it comes back to me
Yeah.
right now.
Okay.
Thank you.
Sure. So Julie, just to answer your question, your degree of freedom is always present on your formula sheet. So it's not something you have to remember by heart. So just check the formula sheet and you're good to go.
Yeah, I see it in the formula sheet, but is it, so you do 249 times 249?
No.
I thought you said it was, the row was the same as n. Maybe I remember it wrong.
So remember, guys, you need to make sure that you are very clear on the difference between the two chi-square tests. So this is the goodness of fit test, which means there's one variable. So your degree of freedom is number of categories minus 1. That's it. So it would be 3 minus 1 is 2. When the degree of freedom has the number of rows multiplied by the number of columns, there's rows and columns because there's 2 variables present. Okay, so in this case, the degree of freedom is just 3 minus 1. Does that make sense? Do you see it in the formula sheet? Number of categories minus 1.
Wait, but we're doing tests for independence, right?
No.
Oh,
The test for independence has 2 variables, and it's about a relationship between the 2 variables. There's only one variable here.
oh,
Yeah.
okay.
Okay. I'm gonna show the solution, but Julie, I do encourage you to just do the calculation anyway. Next. Okay. Okay, so it is a chi-square, goodness of fit, because there's only one variable, the number of music festivals attended, and it is measured on an ordinal level. Okay, none, 1 to 3, more than 3. Your H0 should have been copy-paste those percentages that were given, and your H1 is that it is not true that, yada, yada, yada. And we would reject the H0 and accept the H1 because we look on the right-hand side, our chi-square obtained is 37.75, and our chi-square critical would have been 5.99. So obtained is greater than critical. Did anybody, obviously besides Julie, because you did a different calculation, did anybody have any issues doing this question?
I do have this calculation. I don't know.
Okay, so you just
I'm very confused.
got confused with the names of the test, then that's
Yeah.
that helps. Yeah, okay, cool.
Okay.
Yeah. But yeah, is everyone good with the chi-square goodness of fit? Yeah, lovely. Okay, it's that time again. We've been at it for an hour again already, so take 10 and let's see what the time is now. I will see you back at 12:40. Okay, so 13 minutes. Is everyone back? Good stuff. All right, more practice questions. Let's keep going. Okay, 2 parts to this question. The first part shouldn't take too long. So tell me when you're done. Okay. Let me pick someone and be rude. Maybe Julia. Julia, what answers did you give for this?
Me?
Yeah, you.
I at first I was a bit confused, but then I thought two sample the two sample t-test
Mm-hmm.
because of we have two groups and we have an interval ratio variable, which is the average satisfaction, and we have the ordinal or nominal, like we have the groups, the two
Mhm.
groups, if they voted or not. And then for the hypotheses, I have for the HO that they do not differ and for the H1 that they differ.
Okay. Yes, correct. Did everybody else see that? Did anybody have issues with this? I'm glad you were able to work your way out of confusion. It happens sometimes. When we first read it, it's a bit, good job. Essentially, when you read this, what I would like you to be able to see is that essentially we're doing a comparison between people who voted and people who did not. Okay, so comparison already indicates a one sample t-test, sorry, not one sample, a two sample t-test or an ANOVA, but there's only two options. It's voted and didn't vote. So it would be a two sample t-test. Okay, and your hypotheses, even though Julia, she did it as in they don't differ and then they do differ, you can also say that your H0 can say that they're equal in their average, and your H1 that they're not equal in their average. Lovely. Let's move on. Sorry, guys, got distracted. Didn't see your messages. I told you I can get lost in my own head. You need to unmute sometimes. Cool. Who wants to tell me what their answers are? I'm going to have a more active session now.
can do it, I think.
Okay.
So for the hypothesis for the Levene's test, I wrote down H0, the variance of the two groups is equal. And then as H1, the variance of the groups is not equal.
Okay. Can I pause for a quick? I want to get a sense from you guys when you're answering these questions and you're writing down the hypotheses, are you actually writing the variance of the two groups is equal? Because you do need to be specific. You can't just say the two groups. You need to actually say what the groups are. But I don't know if you're just doing that to be efficient
Okay.
when you're telling me. This is true of the other hypotheses as well.
Okay. No, I wrote it down as two groups.
Okay.
I think also to be short, but I will keep in mind to name the groups.
Okay. Yeah.
Then question 2 also.
Yeah, go for it.
So the p-value of Levene's test is 0.739. That's higher than alpha. So I wrote there's a significant difference in variance across, well, yeah, the two groups, but then the.
Okay, so let's go back to your interpretation. So you said that the p-value is higher than alpha.
Oh, wait, so there's no significant difference then.
Right, so that means you retain the H0.
Yeah.
Right.
Sorry,
Okay.
that's sloppy of me. Yeah.
Okay.
So H0 is retained, yes.
Yes.
Um,
And I want you guys to keep it simple, right? So retain the H0, which means you retain equal variances assumed. Or you can assume equal variances. Yeah. Okay.
okay. Wait, I'm gonna write it down.
Okay.
And then for the last one, the test statistic of the t-test is I had 16 point. Oh wait, yeah. So I wrote down the wrong. I assumed the wrong Levene's test. So it should be equal variances assumed. So 16.107. And then the two-sided p, because it's non-directional, is lower than alpha. So H0 is rejected, and in the population, the population mean is not equal. Yeah, I wrote it down like that, but I'm just being short because I don't want to write too much, but across the two different groups.
Yeah, absolutely correct. Okay, regarding the specificity of hypotheses. Okay, so it's just when teaching, because hypotheses can sometimes be a bit wordy, it's just annoying to say them out every single time. That's why I say things like the two groups are equal. But I'm just going to go back to a solution from a previous question so you can get a sense of what the hypothesis should actually look like. So in this population, people who voted in the last election do not differ significantly from those who did. From people who did not vote in their average satisfaction with their national government. Okay, so notice that you start with in the population. I actually say the full thing of what groups are being compared, and I actually describe the groups. I mentioned that average satisfaction, so it's important that it's population average that's being compared, and the dependent variable satisfaction with their national government. So in your hypotheses, all your variables need to be named. You need to make sure that you mention that it's in the population, and if it's dealing with a population average, that has to be mentioned as well. So for your population variance, so your Levene's test hypotheses, which I will have on the next slide, but just to show you. Okay, so your H0 is that in this population, the variance in satisfaction with their national government is equal for both voters and non-voters. So see, I found a quicker way to state voters and non-voters, right? The variance in satisfaction is not equal for both voters and non-voters. Okay. Everyone good with this? I'm not getting any thumbs up, but if you don't want me to move on, unmute yourself and tell me. Okay, we're good. Lovely. Question 5, here we go. Okay, Julie, you're a bit stuck. What's going on?
I mean, I don't think it's too hard or something, but I just don't understand my own notes that I wrote down. So I
Mm,
don't really know what steps to do, um,
okay.
and in what order.
Okay, well, you're able to identify the test to start with.
Yeah, I chose the test for independence.
Yes. Okay, good. Um, and you've got your hypotheses, I'm guessing, as well.
Yeah, as H0, there's no relationship between a teenager's biological sex and number of hours of sleep, and then as H1 there is a relationship, yada
Yes.
yada yada.
Yep.
But then with 3, because I've been very sloppy with my writing today, so I don't really understand the notes to
All right.
start.
So step one is because in the text of the question, you were not provided any percentages to work with, or expected, your expected frequencies or expected percentages. So step one is you've got to calculate your expected percentages using the total column.
Yes.
And you know how to do that.
Yeah.
Okay. So you would have 3 percentages here on the right-hand side. Then step 2 is you need to take your first percentage and multiply it with each column total. So
Oh, yeah.
yeah. So is everyone okay for me to just go into the solution? It'll be much easier to talk about it. I think, yeah, people seem done. Are people done? Julia is done. Is anyone else done with this? Ready for solution? I don't want to show you the solution before you're done. Okay, but Julie, you know what to do, so you can continue with it now. Cool. I'm gonna wait on everybody before we move forward. Okay, can everybody give me a sense of where they are with this question? I've got a couple of people who've told me they're done. How about everybody else?
I'm summing up them now.
Sorry, I missed that.
I'm summing up the answers
Okay.
now.
Okay, perfect. I'll give you one more minute, okay? Okay, let's have a look at the conclusion, the solution. Sorry, it's in image form. Okay, first question, it's a chi-square test for independence. Your H0 should be that in the teenage population, there's no relationship between biological sex and sleep duration. And H1 is that there is a relationship. Okay. What else? You can see all the calculations there. Boring, your chi-square obtained should have been 3.3, and your chi-square critical should be 5.99. So the obtained is smaller than the critical, which means we retain the H0, that there is no relationship here. Did we all get this right? Give me a thumbs up if yes.
I didn't get it right.
You didn't, Julia, no.
Yeah, I have the right critical value, and I also have the right starting percentages, but I think something in my calculation went wrong because my end yes, X obtained is wrong.
How far off is it?
I have two. Is that so? I have so I did it for the male and I did it for the female.
Okay.
And I did it separated and then step by step with the table.
Great.
And then I got for the man like 1.81 and then for the woman 1.49. Wait, which could
The solution. I'm a little bit lost now.
No, I think I have it. I'm sorry for the confusion. I think I have to sum up the man and the woman together?
So the way it works is that you basically have to do each block in the table on its own. So for females who sleep 7 to 10 hours, right? You've got an FO, which was 3, and the corresponding FE was 4.95. So you've got to do this thing on the right-hand side on this FO minus FE squared divided by FE, right? That's only for females who sleep 7 to 10 hours, and you get your 0.77. And you need to do it for every single block. Okay, so in this crosstabs, you've got 6. Do you see that? Do you see what I'm talking about?
Yeah, I did it separately. So I didn't add up the female and the male results. So I have the same results, but I didn't add them up. Like I just add up the females and had a score for the female, and I did add up the male and I had a score for the male.
Right. And then you can just add them together because you would add them all up anyway.
Okay. Okay, yeah, then it's right.
Okay.
Okay, yeah.
That's a grave mistake. Okay,
Okay, thank you.
sure. Anybody else? If you got it right, please give me a thumbs up. I really would like to see. Great. This is really good, guys. Good stuff. Okay. We only have 5 minutes left, and I think this was the last question. Okay, I did put extra questions just in case we had more time, but there's no use starting something now. I think we're gonna cover these questions maybe tomorrow. So the way tomorrow is gonna work is I'm gonna do some teaching time for regression. And then we're going to do a lot of practice tomorrow because the whole point is to mix and match all the questions, right? Because the way we've been doing it is that I teach you probability and then we do a practice probability question. So we're going to mix and match all the questions from all 7 weeks, and so that you can identify them in the mix and then go about them. And it's just going to be doing it over and over and over again until it feels second nature to do it. Okay, so it feels more boring than difficult to do the questions. Yeah, and as usual, based on now the 6 out of 7 weeks of content that we've covered, how are you feeling about this exam? Okay, these are decent numbers, 7, 8. Okay. Cool. So, like usual, I want to know what makes you say 7 or 8 instead of like a 9 or a 10 based on these 6 weeks of content. Does anyone want to share?
So for me, like,
Mhm.
because I know what we're doing, I would know, and also I can check my notes if I get stuck. So I just
Mhm.
need to practice the steps that I need to do.
Okay. Okay.
I think I also just need more practice. Like I couldn't fully do it without my notes right now. I'm always have to like kind of look.
Okay. All right. My challenge then to you guys for tomorrow's session is to spend some time this afternoon, tomorrow morning, whenever you have a moment. Do some studying, okay? And tomorrow I challenge you to not look at your notes when we do basically a kind of a mock exam. Okay. Because that'll give you your best indication of where you're going to be in this exam. Another thing is I know that self-doubt plagues students, especially if they do struggle with this course, is that because you think like you're bad at this course or you're bad at math in general, you don't ever think you're right about something. And that is something I also want to kind of get out of your system, is that there are concrete ways to know that you're right. And you guys have done really well throughout these trainings. So I have high hopes for you. All right, I think that's it then. That's everything. And I'll see you tomorrow. Congratulations on this marathon of a training.
Thank you. Bye.
Thank
You're
you. Bye. See you tomorrow.
You.